Galaxies spin. In fact, they spin so fast they should tear themselves apart, shedding their stars outward into the void. To keep them intact, there has to be an enormous amount of invisible mass holding everything together. In the 1970s, astronomer Vera Rubin provided the first undeniable evidence for this unseen glue. Using optical telescopes, she painstakingly tracked the orbital speeds of stars in nearby spiral galaxies. When she mapped the Andromeda galaxy, she found a problem. The stars at its absolute outer edges were orbiting at the exact same high speeds as the stars tightly packed near its core. Rubin's measurements established the standard model of cosmology, a framework built on a delicate balance. In this model, dark matter pulls things together through gravity, while a separate force known as dark energy pushes the universe apart. It provided a mathematically neat and elegant framework. Physicists could plug in the numbers, run the equations, and accurately predict the behavior of a safe, seemingly solved cosmos. But the era of looking through eyepieces has given way to instruments of massive scale. We now have the James Webb Space Telescope scanning the first galaxies, the DESI project mapping the cosmic web, and the underground LZ detector hunting for physical particles. Instead of confirming the standard model, these next-generation instruments are capturing data that breaks the established rules of physics. Astrophysicists are wrestling with three major paradoxes: galaxies completely lacking dark matter, stars that defy standard formation timelines, and physical constants that refuse to stay constant. The old equations no longer balance. To understand reality, researchers are being forced to abandon those mathematical comforts and embrace radical, violent new theories about how the dark universe operates. The first anomaly takes us to a string of ultra-diffuse galaxies, including a recent discovery known as DF9. Astronomers measured the stars in this galaxy and found an exact match for the visible mass. There is no dark matter there at all. If dark matter were simply a universal rule of gravity holding everything together, a galaxy couldn't just choose to opt out. The laws of physics apply everywhere equally. To explain the missing mass, researchers point to the bullet dwarf collision theory. It suggests these strange, naked galaxies are the debris left over from violently fast collisions in deep space. Imagine two gas-rich dwarf galaxies hurtling toward each other. The giant gas clouds physically run into each other and stop, merging together. But the dark matter halos, which only interact through gravity, pass straight through one another like ghosts and leave the collision zone behind. This physical separation disproves theories like modified Newtonian dynamics, or MOND, which argued that dark matter was merely an error in our math equations for gravity. Paradoxically, finding a galaxy with absolutely no dark matter is the ultimate proof that dark matter is a distinct physical substance, one that can be violently stripped away from the normal matter it used to hold. The James Webb Space Telescope has uncovered a second anomaly during the cosmic dawn. It has beamed back images of incredibly bright blue monsters and mysterious little red dots hosting black holes that are far too massive for their age. This chart maps the maximum possible star mass since the Big Bang. The JWST data point sits completely disconnected, showing black holes growing far larger than standard evolution allows. Normal cooling gas cannot account for this growth, requiring an entirely different fuel source. Physicists propose a radical solution: dark stars. Instead of running on nuclear fusion, these theoretical objects grow to enormous sizes by feeding on the energy released when dark matter particles physically crash into each other and annihilate. Dark matter acted as the explosive fuel for these objects, providing the seeds for the most massive black holes ever observed in the infant universe. The third anomaly involves dark energy. A century ago, Einstein introduced the cosmological constant, an assumption that dark energy is a uniform, unchanging force pushing the universe apart at a steady rate. Now, a project called the Dark Energy Spectroscopic Instrument, or DESI, has released a massive 270 terabyte three-dimensional map of the expanding cosmos. This chart shows the cosmological constant as a flat, steady threshold line. But when we map the new DESI data over it, we see a fluctuating, downward trending wave. It shows that dark energy's influence appears to be withering and evolving as cosmic time progresses. If the density of dark energy is dropping, the long-held assumption that the universe will expand at an accelerating rate forever is no longer guaranteed. The ultimate fate of the universe is no longer a fixed mathematical certainty. It is a dynamic and highly unpredictable open question. While telescopes look outward to answer these questions, physicists are also hunting on the micro level. A mile underground, deep within the terraced depths of a former gold mine in South Dakota, sits the Lux Zeppelin detector. The LZ team monitors 10 metric tons of ultra-pure liquid xenon. By operating so deep underground, they can filter out the background noise of solar radiation, the neutrino fog, to try and capture a direct physical collision with a dark matter particle. They are waiting for a silent, invisible strike. If a particle hits a xenon nucleus, it deposits energy and forces the atom to recoil, triggering a brilliant, localized flash of light that finally proves the particle's existence. The dark universe behaves as a dynamic, physical substance. It fuels the earliest stars, strips the gas from colliding galaxies, and dictates cosmic expansion. Vera Rubin established that the invisible universe exists. Now, the goal is to physically detect those particles and map how they govern the visible matter we see across the night sky. This is NGC 1052-DF2. It's an ultra-diffuse galaxy, an object with the massive physical footprint of the Milky Way, but almost none of the density. It is so sparse that you can see older, more distant galaxies shining from behind it, as if looking through a thin fog. Kinematic measurements of this string of galaxies revealed a cosmic anomaly. They appear to be missing their dark matter entirely. This discovery creates a contradiction that seems to defy the last 50 years of physics. If dark matter is the invisible glue holding galaxies together, we must explain how finding one without that glue proves the substance exists. Solving that puzzle requires us to look past the light we can see and reevaluate the invisible forces that dictate the structure of the universe. In the mid-20th century, Vera Rubin was an astronomer working at the margins of her field. She was routinely denied access to advanced telescopes based solely on her gender. She eventually found a home at the Carnegie Institution, where she began studying how galaxies move. Rubin measured the rotational speed of stars at the extreme outer edges of spiral galaxies like this one. She expected a drop-off in speed, a natural slowing of orbits as stars moved further from the dense gravitational pull of the galactic center. Instead, she found these outer stars were whipping around as fast as those near the core. According to the laws of gravity, these galaxies should have flown apart, unable to hold on to stars moving at such high velocities. Her data proved that an immense amount of invisible mass must provide the extra gravitational pull. This established dark matter as the physical scaffolding that keeps the cosmos from tearing to pieces. Not all physicists were convinced that an invisible particle was the answer. Some argued for a theory called modified Newtonian dynamics, or MOND. MOND posits that we don't need a new form of matter. Instead, it suggests that the fundamental laws of gravity simply change on a cosmic scale. In low acceleration environments, MOND argues that gravity naturally pulls harder than our standard equations predict. This brings us back to our dark matter-free galaxy, DF2. If MOND is a universal law of physics, its rules must apply to every object. Because DF2 is so sparse, MOND predicts its stars should move at high speeds, caught in that extra pull. But observations showed the stars in DF2 moving at a sluggish pace. They were following the standard rules of gravity, as if the extra force predicted by MOND simply didn't exist in this specific part of space. This creates a fatal problem for the theory. A galaxy cannot choose to ignore a fundamental law of nature. If gravity itself were modified, every galaxy in the universe would show that extra pull. The normal gravity seen in DF2 demonstrates that the extra pull seen in other galaxies isn't a rule of physics. It's a physical substance that can be present in one galaxy and entirely absent in another. If dark matter is a physical substance that provides a galaxy's scaffolding, we have to ask how that scaffolding can be stripped away. The answer lies in a violent event called a bullet dwarf collision. It begins with two gas-rich dwarf galaxies hurtling toward each other at millions of miles per hour. As they collide, the dark matter halos pass straight through each other like ghosts. Because dark matter only interacts through gravity, the particles from one galaxy don't physically hit the particles from the other. But the normal matter, the giant clouds of gas, cannot pass through. They smash together like a cosmic brick wall, instantly halting their forward motion in a massive shockwave. This impact separates the gas from its fleeing dark matter. The sudden compression of that gas triggers a burst of star formation, creating new galaxies in the empty space between the two departing halos. These new galaxies are the wreckage of the collision. They are left behind with no dark matter at all, providing forensic evidence that normal matter and dark matter can be decoupled. The existence of galaxies like DF2 changes dark matter from a theoretical placeholder into a tangible, separable substance. This confirmation allows us to understand the early universe. Shortly after the Big Bang, dark matter clumped together first, creating the gravitational wells that pulled in ordinary gas to form the very first stars. We are now mapping this early distribution using the mirrors of the James Webb Space Telescope. We can see how dark matter's gravity organized the large-scale structure of the universe long before light could even travel through it. By triggering star formation earlier than ordinary gravity could, dark matter provided the time needed for stars to fuse heavy elements. Without that head start, the universe might not have had enough time to forge the materials required for planets like Earth. These modern breakthroughs are the direct result of Vera Rubin's persistence. She spent years defending her work to a community that was often more skeptical of her than they were of her data. Her choice to look at the ignored edges of galaxies revealed a structural secret that had been hidden in plain sight. We have tracked this mystery from Rubin's first rotation curves to the violent decoupling of the bullet dwarf collision. Each discovery has confirmed that the universe we see is held together by a vast universe we cannot. Identifying this invisible substance provides the framework for understanding our history. By studying the galaxies that lack dark matter, we have finally confirmed the nature of the scaffolding that supports everything else.